Hi, everybody. Welcome to week 3 for Kin 376. Uh, for this week, we're going to have 3 lectures. We're going to be talking about linear kinematics, angular kinematics, excuse me. And then we're going to have a small lecture to review for exam 2. So by the end of this week, we'll have 3 lectures, and there will be your second exam. And then there was also an assignment as well, another 25-point assignment, which is essentially an acceleration lab. I'm having you, I think you're going to be running up some stairs and you're going to be calculating your acceleration. I will also release a video to explain that as well. We'll have a weekly Zoom meeting if you guys need to ask questions. And then obviously, after watching these and doing a little bit of studying, if you still have questions on this stuff, feel free to email me, feel free to contact me. I'm very happy to answer any of your questions. And if we can't do it through email, we can do a individualized Zoom meeting. So we're going to start getting into kind of some more mathematics in this class. As just a disclaimer, when we're getting into math and physics, I like math and physics, so I tend to go off on some tangents every once in a while. I'm going to try to limit them the best I can, but just, full disclaimer, if I get on a tangent, just bear with me. I'll make sure it's not too long. But when we start looking at the math and physics, especially in kinematics and kinetics, none of this stuff is really too complicated or tough. It's not too advanced. We're essentially looking at how to calculate velocity and acceleration, and then the difference between distance and displacement. They're fairly straightforward concepts, and so today we're looking at linear kinematics. The next lecture we'll be looking at angular kinematics. Essentially, linear and angular kinematics, the only thing we're really changing as far as how we calculate these values is we're really just changing the units. The equations are pretty much the same equations. The concepts are very, very similar. Really, all we're doing is we're changing the units. We're just changing different symbols. So it's not really too complicated, or at least I hope it's not. So let's talk about why we look at linear kinematics. Good kind of case study is we want to look at kinematics to describe or even kind of come up with a reason why Usain Bolt may be the fastest man alive. This video right here, I can't show it for this lecture, at least not through PowerPoint directly. A lot of the videos, actually I think all the videos in this lecture are on YouTube, but they were posted through the International Olympic Committee, and they put a weird sort of copyright on it. So if I tried to present it through PowerPoint, it gives you an error saying, oh, this is copyrighted, you can't do that. But the links are embedded in these sorts of way. So if you just hold Control and click on the links here, it'll take you to YouTube and show you the video itself. These are all pretty interesting videos, and they really do help illustrate the importance of kinematics and what kinematic values are and why they're important. Especially this first one here, they go through how Usain Bolt, how his velocity and acceleration are different than a lot of sprinters, and how the mechanics of his body, especially his trunk, we see little motion in his trunk, and how he's able to change his stride length and stride frequency puts him at an advantage to other sprinters. So it's a very, very interesting video. This second video here, I like posting, as you'll notice I said Usain Bolt may be the fastest man alive. This second video, it doesn't really go too much into kinematics or anything like that, so it's not really required reading, so to speak, for the exam. But it's interesting the same. It's a TED Talk done by a statistician, and he poses the question, are humans, are athletes really getting bigger, stronger, faster? And the kind of common conception is that, um, they are, that the athletes today are better than the athletes 10, 20, 30, 40 years ago. And while we see that if we're looking at just the performance outcomes alone, that holds true. And then some people make kind of the mistake as well, humans are evolving somehow and everything like that is, and that's technically not true. Evolution takes a long time to happen, and Homo sapiens is as far as humans are considered, really they're not. We haven't really been present on the earth for as long as we'd like to think. There's been other animals that are even alive today that have been here a lot longer than us. So we're technically not evolving and getting better, stronger, and faster. What he does is he looks at factors such as better equipment, better nutrition, better training, which is needed for, which biomechanics is needed for, and he actually factors those out and he actually determined that Jesse Owen is in fact still about I think it's just less than a quarter a second faster than Usain Bolt. So in my opinion, his record still stands. But and if you don't know who Jesse Owens is, he was an Olympic sprinter, and he broke the Olympic sprint record in, like, I think 1938 at the Olympics, and I still think his record holds. But once again, that's kind of what we're looking at. Well, that's why biomechanics is useful. This is why sports science is useful. It allows us to learn about certain concepts and laws so that we can help train athletes better, like Usain Bolt. Come up with better shoes, come up with better running shorts, come up with better training and teaching of movement so that they are much more efficient, so that they can actually run faster. So let's get to the kinematics. When we say kinematics, we are looking at the description of motion without considering the cause. The cause of a change in motion, or the cause of motion, or the cease of motion, are forces. And we'll talk about that in next week when we start looking at kinetics. Kinetics is the study of forces, or the study of cause of motion. Okay? For motion to occur, or for it to be modified in any way, we're looking at the summation of forces. Kinematics, we're just looking at describing the result of forces. So we're looking at velocity, acceleration, displacement, concepts like that. And the concepts we're talking about, once again, are kind of our linear displacement, or at least for this lecture, we're looking at linear displacement, linear velocity, and linear acceleration. What we're looking at next lecture will be the angular displacement, angular velocity, angular acceleration. These are talking about describing motion that occurs in a rotational manner. Instead of a straight line manner, we're looking at motion that's rotational. Once again, the good news is that these concepts here, as far as how we determine these, how we calculate them, what sort of physics are involved in determining them, are not any different than their linear components. All we're really doing is basically changing units. They're not any more complicated or strange than their linear components. When we look at linear displacement, we're using meters. When we look at angular displacement, we're using degrees or radians. All the calculations for them and concepts and principles are exactly the same. All we're really doing is changing units. So it's not any different or any more advanced or complicated than their linear components. So in kinematics, what we like to do is look at kind of a stick figure or free body diagram of the body in question, whether it's a human, whether it's an object. A lot of times, what we learned from the last few lectures is we like to look at kind of a system. So a body in space could be a system, and the limbs are segments of that system. If we look at a free body diagram, essentially what we're looking at is we see the position of a system or body in space. So when we look at the whole system, we may be looking at linear displacement as far as how much displacement that system has done. If we want to look at the joints, when we look at the system, we could be looking at the whole body, we could be looking at just their legs, and how that changes in space in a linear fashion or a straight line fashion. But without, angular displacement of the joints actually moving or rotating around a joint within a plane and around a joint, which is the axis. That's what we're looking at when we start talking about angular displacements. We're looking at how do these specific angles change, okay? And we use this to determine velocity. We must see more than one frame to determine velocity, okay? Or acceleration. A change in velocity is called acceleration. Velocity, to see a change in velocity, we must see at least 2 frames if we're videotaping it. We have to have 2 reference points or point in time to actually determine a change in velocity. So in linear kinematics, we use these quantities, we use these kind of concepts to determine different things. Why is a sprinter's acceleration close to 0 in the middle of the race? Well, usually when we're looking at a sprinter, in the middle of the race, their velocity isn't changing. They're traveling at a consistent velocity. If velocity isn't changing, we have no acceleration. At what angle should a javelin be thrown to maximize distance? At what angle should a ball be thrown to maximize speed? This is where we start looking a little bit at trigonometry. We'll start looking at, when we look at projectiles in general, the best angle to throw a projectile to maximize height and linear displacement, as far as how far something will go, is we throw it at 45 degrees. And that's where we start playing with our cosine and sine trigonomic functions, and it helps us determine that. We can also say, well, if 2 balls are at the same height, one is thrown horizontally and the other is dropped, which one hits the ground first? Well, according to classical physics, they should hit the ground at approximately the same time. So we use kinematics to describe the motion of these stuff, and it helps us do some prediction of motion as well. And we'll talk about that stuff today. Let's talk about linear kinematic values, or the actual quantities that we measure in linear kinematics. Once again, these are equivalent to the angular components as well. They're angular kinematics. So let's look at our 3 main kinematic quantities. We have distance and displacement, speed and velocity, and acceleration. As we'll talk about on the next slide, it's important to make a distinction between what a scalar and vector quantity is. So when we look at these 5 kinematic quantities, whether they're linear or angular, they are shared between linear and angular kinematics. Once again, we're just changing the unit. Distance and speed are what are considered scalar quantities. Or, scalar quantities or scalar units, whatever you want to call them. Scalar quantities only have a magnitude. Okay? So, distance is only measured in meters. Speed is only measured in meters per second, miles per hour, whatever units you want. We use metric for this class, so we're just using meters. These other 3 right here are what are considered vectors. Vectors have both a magnitude and a direction. What that means is they share a magnitude like within scalars, but they also are dependent on the direction of a system. Okay? So we'll look at an easy one, is the difference between the scalar quantity of speed and the vector quantity of velocity. With speed, you only know how fast a system is moving. Let's say you're in your car and you're looking at the speedometer, which rightfully, aptly named, only measures your speed. It says you're only doing 70 miles per hour if you're on a freeway, okay? Velocity would state that you're doing 70 miles per hour, but in a direction. So you're doing 70 miles per hour going north or going east or going south or west. Okay, so if you had a velocitometer in your car, which is what GPS units kind of use, is they'd say you're going 70 miles per hour east. Or if you're jumping up and down, you're jumping up at 3 meters per second up, or you're falling at 3 meters per second down. So vectors have a magnitude and a direction. That's a very, very important distinction, especially when we start looking at acceleration. Acceleration, and we'll talk about this some more, acceleration is a change in velocity over time, okay? So we see acceleration when there is a change in velocity over time. So you can have an acceleration if the magnitude of velocity increases, if the magnitude of velocity decreases, or if the direction component of velocity changes. So you could be heading 70 miles per hour and then you slow down to 50 miles per hour. There's an acceleration. You were then traveling at 50 miles per hour and you sped up to 70 miles per hour. That's an acceleration. You could have been traveling at 70 miles per hour west, and then you turned your steering wheel and now you're heading 70 miles per hour north. You've changed your direction. So there's a change in velocity so that there is an acceleration. It's a very important distinction, especially when we start looking at kinematics. And once again, I would not be surprised if you were to see some sort of question on the second exam which asks you how velocity and acceleration are kind of tied together in that kind of way of what is the difference between a vector and a scalar? How can velocity change? What do we call a change in velocity? We call it acceleration. Questions like that. I would be very, very, very surprised if you did not see questions like that. So kind of important thing to keep in mind. So let's get into a little bit more detail between a scalar and vector quantities. So a scalar quantity only has a magnitude. It does not have a direction. Vectors have both magnitude and direction, okay? This vector is kind of represented by an arrow, okay? With the length of the arrow or size of the arrow kind of indicating the magnitude of that vector, and the arrow tips indicating the direction of that vector, okay? So we can see here we have the bold line right here. It has a longer kind of stem to it. So we'd say it has a greater magnitude than this other smaller one here. This vector is pointing up and to the left. This vector is pointing up and to the right. So they have different directions, okay? So let's talk about our three of our main kinematic values when we start looking at kinematics. We have time. Time certainly has a magnitude. 5 seconds is greater than 2 seconds, stuff like that. Does it have a direction? For this class, we consider that it does not have a direction. However, if you were to say this to somebody that kind of is a little bit of a nerd, or somebody that's they made an entire career out of physics and explaining time, and they may have come up with a principle called special relativity, this man right here would not necessarily corner you, but he would approach you and in a very calm voice sit you down and spend hours upon hours telling you how wrong you are. yes, time does have a direction. Um, if you are, the faster you go, the slower time goes. Okay, this has been proven time and time again. His whole theory of special relativity, which is commonly accepted, states that yes, time has a direction. This has been, this was proven, this was actually demonstrated, demonstrated many times, but one of the more poignant demonstrations was, I believe it was during the 80s. There was a cosmonaut, and his mission was to go up into space and rotate or orbit the Earth for, and he orbited the Earth for about, I think, 10 hours or so. This is when we're still getting used to going up into space, um, or at least low altitude orbits or high altitude orbits, not really space. And he kept a timer with him. And then the people, then, you know, the Russian Space Energy also kept a timer with them, and they were synced with each other. He orbited the Earth so many times at such an increase. He was constantly accelerating. He was orbiting Earth. By the time he landed, they looked at both timers and they found that his timer was like 0.00002 seconds slower. So in fact, he actually went into the future. So yes, time has a direction. Especially this guy would say too, if you're orbiting a black hole or you're close to a black hole, time does really, really funny things. Not sure what Mr. Tyson would say about that. Probably just tell you something about Pluto not being a planet and how it's not really his fault. But if you were to say that in front of somebody that kind of into physics, they would not be happy with you. However, for our consideration, we consider that time does not have a direction, and we're happy with that for this class. So tangent over for that one. So we can see for this class in biomechanics, in undergrad biomechanics at UNCG, time has a magnitude but not a direction, so that makes it a scalar quantity. Acceleration, however, has both a magnitude and a direction. That's because, once again, acceleration is a change in velocity over time. So since velocity is a vector, then acceleration has to be a vector. And then mass, once again, mass has a magnitude. Something is X amount of kilograms, but it doesn't really have a direction. Once again, you could talk to possibly a theoretical physicist and they might talk your off about they're looking really hard into that, and that might not be true. Once again, for Kinesiology 376 at UNCG, we consider mass to be a scalar quantity. It only has a magnitude, does not have a direction. So let's continue on here. Let's look at the difference between distance and displacement. Distance is measured along the path of motion. It's a scalar quantity. It only has a magnitude. Displacement, however, is measured in a straight line from position 1 to position 2. It's a vector, okay? When we look at velocity, velocity is simply displacement over time, okay? What I've kind of done, what I do a lot when I write this stuff out is just so you can kind of follow along with kind of, you know, the way I use notation is usually with distance, I'll use a capital D. Displacement, I'll use a lowercase d. Velocity is simply a change in displacement over time. So distance may use speed, a change in speed, or, you know, it's not even really measuring speed, but distance is a scalar quantity. Displacement, because it's used for velocity, is a vector. So let's look at kind of an example here. We have this hockey player, and they're traveling from point A to point B, and they kind of did this little curvy path right here, okay? This curved path is what we measure is their total distance, okay? However, if we were to draw a line from the first point to their end point, this is our displacement. So commonly, we'd say that displacement can never really be greater than distance traveled, okay? But when we start looking at calculating velocity, it's important to remember you're looking at a change in displacement, and it is a vector. Let's take a look at another example here. We have a runner on a 40-meter track. After one lap, what is their distance? Well, their distance is 400 meters. Okay. What is their displacement? They started here, and then they ended here. They started and stopped at the same point in space. So what is their displacement? Their displacement is 0 because they started and stopped at the same point. And we'll talk about that. We'll get a little bit more into that. That's kind of important because it'll lead one of our discussions when we start talking about angular displacement. So his distance is 400 meters. His displacement is 0, okay? Because he started and stopped at the same point in space. So for a given movement, distance and displacement may be equal, or distance may be greater than displacement, but displacement cannot be greater than distance. So let's look at a third example, okay? Let's take the case of a cross-country skier. For this activity, they started at 0 kilometers. I need my pen. They started at 0 kilometers and finished 2 kilometers away. So what is their distance? Well, they started at 0, ended at 2. So it's 2 kilometers. What is their displacement? Now ask yourself, is this spot different than this spot? Yes. So their displacement is also 2 kilometers. Okay, they started and stopped in different places. So we do see a displacement of 2 kilometers. So distance can be greater than displacement. Displacement can be equal to distance, but displacement is never greater than distance. And distance is a scalar quantity. Displacement is a vector quantity. So now let's look at kind of speed and velocity. So speed is the distance covered by the time taken to cover it. It's a scalar quantity. Speed is distance over time. So we say S equals D over change in time. Okay? The little delta signal right here just simply means a change in. Delta means change. So we can start applying some of these concepts to why Usain Bolt is allegedly the fastest man alive, if you watched the second video at the beginning. But one of the reasons, he has a higher top speed, and he reaches the top speed later than others. That's kind of important. That's kind of an important thing to look at is, if he reaches the top speed later than other people, why does that make him faster than them? So we'll kind of get into that. But for, first reason makes a lot of sense. He has a higher top speed. Usually things that have a higher top speed get to places quicker. Let's look at kind of just simply walking, running, jogging, kind of human gait. Okay? Speed is a byproduct of stride length and stride frequency. Adults, so speed is stride length times stride frequency. Adults generally, almost always, walk faster using longer stride lengths and a faster stride frequency, while stride length in children has a greater variability. This is our gait cycle right here. So this is our stance phase and our swing phase, okay? Our stance phase is around 60% of our total gait cycle. A gait cycle is the time it takes for one leg, so we'll just look at this woman's right leg here, to complete both the stance phase and the swing phase, from heel strike to heel strike of the same leg. Okay, so when we start looking at human gait, we are looking at the components of stride length and stride frequency. When we look at runners traveling at a slower pace tend to increase their speed by stride length, but at faster running speed, runners rely more on increasing stride rate or stride frequency. So most runners tend to choose a combination of stride length and stride frequency to minimize kind of physiological cost, to increase efficiency. So we look at elite sprinters, they increase stride frequencies with average stride length compared to other sprinters. If we're looking at ice skaters, they increase their stride frequencies. If we're looking at roller skaters, they may increase their stride length. It kind of depends on what is the most efficient way. Is it either increasing stride frequency or increasing stride length? Okay. Usually if we're looking at roller skates, well, it's more efficient for them to do more hip movements and increase the stride length and increase their frequency. So let's look again at why Usain Bolt maybe, I'm just going to keep doing this because I'm a nerd like that, is allegedly the fastest man alive. Once again, that video is really cool. But let's say, why is Usain Bolt the fastest man alive? Well, he uses fewer steps, but he uses a larger stride length. Okay? So while all these other people are really chugging and they're really increasing their stride frequency, he's increasing his stride length. So this leads us to a small little discussion on velocity. Remember that velocity is a change in displacement that occurs in a given time period, and it is a vector. It has its displacement over time, it has a magnitude and direction. So when we look at this kind of picture right here, we see a kind of a change in velocity. Not really, but let's say the swimmer is moving across the river like this, and then we have our current velocity here. This would be the resultant velocity of that swimmer. Once again, this looks like a right triangle. Maybe if we had some quantities of these velocities, some, actual numeric measures, we could determine any one of these velocities. We could, and we might do that later. So let's talk about the difference in instantaneous velocity and average velocity. Instantaneous velocity is what we talk about. It's occurring at one instant in time. This is like our car speedometer. And average velocity is not necessarily equal to instantaneous velocity. When we look at the winner of the men's 100 meters at the 2004 Athens Olympics, they had a time of 2.85 seconds. So we can calculate their average velocity by simply applying that velocity equals displacement over time. So we have 100 meters divided by 9.85 seconds, and that gives us their average velocity of 10.1523 meters per second. Okay? And once again, here's another really cool video that shows that, and we can talk about it, but it's from the Olympics website, and they don't let me post on here, so you may have to watch that on your own time. So let's do a few other examples here. So let's look at runner 1 and runner 2. Runner 1 took 20 seconds to travel 100 meters. Runner 2 was slower. It took them 50 seconds to travel 100 meters. And we know that velocity is displacement over time. So how do we calculate runner 1's velocity? Well, we know time and displacement, not distance, displacement. Very important, the difference between distance and displacement. So for their velocity, they traveled 100 meters in 20 seconds. So their average velocity was 5 meters per second. Runner 2 took longer, obviously. So they did 100 meters in 50 seconds. So their velocity was 2 meters per second. Okay? So we'd say that runner 1 has a greater average velocity than runner 2. We define velocities in each plane. For linear kinematics, we're only looking at the x and y, or our kind of up and down planes, or left to right and up and down planes, vertical, horizontal motion. Okay? For horizontal velocity, it's the x direction. It's a change in the x direction for horizontal displacement. For any vertical movement, it's a change in the y direction. Okay? When we get into angular kinematics, we talk about angular velocity. That angular velocity, we'll just say, I'll put, just for the time being, I'll just say angular velocity equals a change in the z displacement over time. Okay, that's our rotational plane. Okay, so what are the units of velocity? For this class, they're meters per second. In questions on exam and homework, if it's not stated to use a specific unit, that unit will always be meters per second squared. If it asks you to report it to miles per hour, if it asks you kilometers per hour, kilometers per second, obviously you report it as that. But if it doesn't specify the unit, you are calculating in meters per second. Okay, so let's go back to kind of some trig here and talk about kind of our resultant velocity. Velocity can be resolved into our vertical components. Okay, this right here is our vertical velocity. This right here is our horizontal component of velocity, and we are trying to determine our resultant velocity. So a swimmer decides to swim in open water. Their velocity is 5 meters per second. And the velocity of the current is, once again, this is going to be our horizontal component. This is our vertical component. The velocity of the current is 2 meters per second. We want to determine the resultant velocity of the swimmer. If you've taken, physics, first year physics, I'm sure you've seen a question like this on one of your exams or homework, but we simply use Pythagorean theorem. So we know that a squared plus o squared equals h squared. So our adjacent side equals plus our opposite side squared equals the hypotenuse squared. This is our a squared plus b squared equals c squared. Okay? So all we do is use this to kind of plug and chug and get our answer. So our adjacent was our x component of velocity. This is our y component of velocity. And then this would be, we'll just say VR, okay, for our hypotenuse. So we have 2 squared plus 5 squared. So this is 4 plus 5 squared is 25. So we have 29 equals h squared, okay? So then if we just need h, if we square 29, we have 5.39 meters per second. So this is equal to 5.339 meters per second. Okay? So now let's start talking about a change in velocity. This is our acceleration. What does a positive velocity indicate? We are displacing quicker or moving in a positive direction. Usually we say a positive direction is up or to the right. When we say it's either up and to the right, there's no real good reason up and to the right is a positive direction. When we start talking about angular kinematics, we usually say that Counterclockwise motion is, I'll get rid of that real quick so I can write it a little bit better, is we say the counterclockwise motion is usually positive. There's really no great reason that, but we'll just kind of, we say that it is just so we can have, once again, our kind of common knowledge or kind of common agreement that we're saying, well, these are positive directions, so that we can just say, well, up and to the right is a positive direction. So our negative directions is or our negative velocity is basically we're displacing slower or moving in a negative direction. Usually that's to the left or down. If we're looking at rotational, we're looking at movement in a clockwise motion. And once again, it's like when we just kind of agreed with that. So what does zero velocity indicate? No displacement, okay? Zero displacement, and you basically have 0 divided by x, which would equal 0, okay? Or y or z or whatever you want to call it. Okay, so with 0 velocity, we're looking at 0 displacement, okay? Once again, if you're asking, you know, a physicist or something like that that's really into this stuff, they'd say, well, I mean, you could teleport, but we won't talk about that. So if there's 0 velocity or if there's no displacement, there's 0 velocity. So a change in velocity may represent a change in speed, movement direction, or both. Units of speed and velocity are always length units divided by time units. So since we looked at a change in velocity, we have a new kinematic value or concept or principle, and that is acceleration. Acceleration is the rate of change of velocity, okay? Because velocity is a vector, acceleration is also a vector, okay? So acceleration is a change in velocity over time. Since velocity is equal to displacement over time, a change in displacement over a change in time, okay? And we're dividing by time again, our common units for acceleration, unless it's otherwise specified, is meters per second squared. Or you'll commonly see it written out like meters times second negative 2. It's basically saying, you know, it's basic. This is simply looking at it like this. Okay? So you'll see it mostly like this, but sometimes you'll see it like that. Okay? So acceleration, unless otherwise specified, is in meters per second squared. For acceleration in the horizontal direction, it's ax equals a change in velocity x over a change in time. And for the vertical directions, it's acceleration y equals change in velocity y divided by time. Okay, so average acceleration. We very rarely, at least in this class, will talk about instantaneous acceleration, instantaneous velocity. We usually look at our averages. But we have this guy running, okay? In 1.2 seconds, they start out with a velocity of 4.5 seconds, and then they decided they wanted to speed up, and they finished their run at 8.3 milliseconds, or meters per second, excuse me. So we take V2 minus V1, oops, I almost put initial there. Let's get rid of that. Okay, so, and that's kind of one of those things, usually we say V final minus V initial, depending on who you talk to, but it's usually V2 minus V1 divided by time gives their acceleration. So, they started at 8.3 meters per second, subtract that from 4.5 meters, so this is our change in velocity. Here we're saying V2 minus V1, okay? This should be 2 2, initial 1. Okay, I made a mistake there, but I tried to fix it. Is, what does it say? This is V1, V2, sometimes V final, V initial, excuse me. Okay, so we took 8.3 minus 4.5 meters per second and divided that by 1.2 seconds. So our average acceleration was positive 3.17 meters per second. So we can assume their average acceleration AVG for average acceleration is positive. That means they sped up. So let's look at what determines positive acceleration, negative acceleration, zero acceleration. We'll take our first example here. We had a positive acceleration. If, let's say, they did their entire foot race, and their velocity at the end and in the beginning was both 12.5 seconds, 12.5 minus 12.5 equals 0. 0 divided by 0.8 is 0 meters per second squared. We have a constant velocity. So if acceleration is 0, then velocity, or at least a change in velocity, is also 0. We have a constant velocity. If acceleration is positive, that means we have a positive change in velocity. So we have a positive acceleration. If, on the other hand, we're seeing acceleration at the end of a race, okay, which we'd call, they started the race at 4.3 meters per second, and then they accelerated to 11.1 meters per second, and they did it in 0.9 seconds, we have a negative velocity, or a negative acceleration, excuse me. So a negative change in velocity equals negative here, so we have a negative acceleration. Sometimes you'll see this say that there is a deceleration. We could just say negative acceleration. So our acceleration, we can have positive, negative, or 0. We haven't gotten into kinetics, but when we do, usually if there is a positive acceleration, that means there's a positive summation of force or resultant force. If there is a negative acceleration, we have a negative summation or resultant force. If we have 0 acceleration, that means all forces are in equilibrium, or the resultant force is 0. Okay, that ties into one of Newton's laws, 3 laws of motion. So why is Usain Bolt, I'll give up, the fastest man alive? He accelerates the fastest and he maintains top speed longer. Acceleration is near 0, but it is never decreasing. Compared to his fellow sprinters, they may have accelerated, but they haven't gotten there. They got to their top speed sooner. Usain Bolt maintains his top speed longer and never has a negative acceleration. So he never slows down until the end of the race where he eventually stops, but you get it. So another way of looking at this, let's think of riding in a car. When we step on the gas, the car accelerates, so we see an increase in velocity. Okay, we see a positive acceleration, we see a positive or increase in velocity. When we step on our brakes, we decelerate the car, so we're looking at a decrease in velocity, so we'll have a negative acceleration. However, as we saw for velocity, depending on the reference frame, a positive acceleration may not mean that the body is speeding up. It may be because of a change in direction. So if this is a nice little kind of thing to work through and kind of keep in the back of your head, write it out a few times on some loose leaf paper and you'll kind of remember it. If we have a positive change in magnitude and a positive change in acceleration, or in direction, we have a positive acceleration. If we have a negative change in magnitude, so we went from high velocity to low velocity, okay, but we did have a positive change in direction, we have a negative acceleration. This would be if you jumped up in the air, as soon as you leave the ground, your velocity starts decreasing. But you are moving upwards, okay? So you have negative acceleration up until you stop moving altogether and then come back down to the ground. Same thing with this. If we have a positive magnitude and a negative direction, we have a negative acceleration. If you're falling, okay, let's say you decided to jump off a ledge or something like that, and you're traveling downwards, you have a negative acceleration. Common one with this is gravity. Gravity accelerates at negative 9.81 meters per second squared. It's pulling you down. And then finally, if you have a negative magnitude and a negative direction, you have a positive acceleration. So what does a positive acceleration tell us? Direction and magnitude are the same sign. They're either both positive or both negative. What does a negative acceleration tell us? Direction and magnitude are different signs. And zero acceleration indicates no change in velocity. That velocity is maintained. So now let's look at projectile motion. Okay? Projectiles are bodies projected into the air that are in free fall. For this class, we will ignore wind resistance or even water resistance if we're looking at somebody in water and stuff like that. We don't care about friction and everything like that. So, good examples of this is throwing a baseball, passing a basketball, throwing a disc, a skydiver, jumping out of a perfectly good airplane. Airplanes, rockets are not projectiles because of forces due to their engines, okay? Technically, a rocket, if we were to call it a missile or a ballistic missile, these start with forces, but they go up really, really high, and then they fall down just to the force of gravity. So a projectile, basically, it has a parabolic path. Okay, I'll try to write that a little bit better. Parabolic path. So in this diagram, where will the projectile fall? Remember, all projectiles have a parabolic. That wasn't great, so let me redraw that. Projectiles have a parabolic path. So if we mirrored this side and simply flipped it to the other side, it's going to land approximately right here. Okay? There we go. How do we know this? Because the projectile is subject to physical laws which are always the same, at least on Earth, especially in Kinesiology 376 at UNCG during the summer 2020 semester. The laws of physics do not change, for this class at least. If they did, weird stuff would start happening. Okay, a projectile has a horizontal and vertical component. When we start looking at shot putting, long jumps, discus, we want to maximize the horizontal component. For high jumpers, pole vaulters, we want to maximize the vertical component, okay, or height and range. So we do have some kind of laws that we use for this. Our vertical component is influenced by gravity. Once again, gravity is 9.81 meters per second squared. It's always this. On Earth, it's always 9.81, or you can use 9.8 because one is insignificant, but 9.8 meters per second squared. Our horizontal component is not affected really by forces except wind, but we are not considering those for this class. Vertical component relates to the maximum height of an object or system. The horizontal component relates to the maximum distance of an object or system. So factors affecting projectile trajectory. We consider our projection angle, projection speed, and projection height. These angle and speed determine our projection velocity. So let's look at our projection angle. This governs the shape of the trajectory when speed and height are constant. So if we're looking at throwing a basketball, okay, we see at different angles, we see different height and different x displacement, or horizontal and vertical displacement. So let's just take a look at these. We see generally the greater the angle, the higher it goes, but the less further it travels. When we start going further and further to a more shallower angle, the vertical displacement starts decreasing and the horizontal displacement starts increasing. But we see at 45 degrees, we get maximum of both, okay? We will talk about that in just a second. Let's talk about projection speed, okay? This governs the size of the trajectory when angle and height are constant. In a vertical jump, height is entirely dependent on the vertical velocity at takeoff. What affects the vertical velocity? The direction of the applied force, which is our muscle strength and coordination. So the greater the applied force, the higher something will go. The harder you throw something to the right, the further it will go. Very simple. Now projection height. This governs the flight time and distance when an angle and speed are constant. If you throw something at ground level, it will travel approximately, let's just say it travels approximately 10 meters. If you were then to get onto a 3-meter ledge and throw it at the same force, let's say it'll travel about 13 meters, so about 3 meters further, okay? Fairly simple. It has greater time in the air to come down and still travel forward. But once a projectile, ball, or person is in the air, the jump height, time, and distance are already determined. If you are in the air, you jump in the air. While you're in the air, you are subject to gravity. For this class, we're only looking at gravity. There's nothing else you can do. So if a projectile is a human body, can we see a change in jump height, time, and distance? Well, no. If a person's in the air, we're looking at just their center of mass travel through air. So why aren't long jump athletes coached to jump at a greater takeoff angle? So we'll look at all of this stuff here. You know what would be a good exercise? Play with the sign of the angle, okay? Even the sine and cosine. But as you increase the angle from 0 to 45 degrees, the sine value gets closer and closer to 1. It's the inverse to cosine, okay? As you increase the angle from 0 to 90 degrees, cosine gets smaller and smaller. But at 45 degrees, we see maximum value for sine and maximum value for cosine, okay? Grab your calculator and play around with different angles and see that as you start to approach 90 degrees, you start seeing a maximum of sine and a minimum of cosine. But at 45 degrees is where we see the maximum of both the sine and cosine of an angle, okay? They're not equal to each other, but that's where we see kind of a happy median where both vertical and horizontal can exist at their maxes. Okay, when a human is the projectile, we follow the center of mass of the body, okay? Therefore, by changing the body's configuration while in the air, you may increase peak height by reaching your fingertips during a jump in basketball, or increase distance during long jumps. So if you stretched out your legs, you get a little bit more distance. This kind of reminds me of a funny story. This is the man, the legend, Calvin Johnson. He was a wide receiver for the Detroit Lions. He was, besides being one of the best wide receivers ever in existence, he was kind of, one of his claims to fame is he had a 3 feet vertical jump. So he could leap off the ground and leap 3 feet in the air. It helped him a lot with, shoddy offensive line where the quarterback has to instantly throw the football and generally throws it a bit higher. So it was nice that he had a 3-foot vertical leap. One of my friends didn't think that was very, and claimed that he could jump higher than that. But when he jumped, he'd bend his legs. He'd basically flex his knees so his knees instead of his feet were off the ground. He said, I can do it fast. Like, that's not how they measure vertical leap. They jump and they keep their legs straight, but they outstretch their arms. It's a stupid anecdote, but that made me think of it, so there's that. He had a max record of 3 feet. He could jump 3 feet vertically. If we're looking at a long jumper, they should hyperextend their shoulder to maximize distance. Shoulder and knees to maximize, well, they can't hyperextend their knee, but if they throw their arms back and stretch out their legs, they can get a further vertical jump or long jump distance. So that's the end of this lecture. I hope I made sense. I hope you understood this stuff. Obviously, if you don't understand everything for this, feel free to contact me and I can help you out any way I can. Goodbye.